We're doing more reactions. 2008 Form A. All right, we have aqueous, which means that we are going to have NaOH, but it's going to split because it's aqueous. And we have a saturated solution, so that means we're going to have some solid aluminum hydroxide. Oh, we form a complex ion. So we already are told there's a complex ion forming. So AlOH, we've just got hydroxide and a hydroxide. The sodium's not going to do anything. Now Al was +3. And remember, the number down here is twice the charge of the metal. So this will be a 6. Now we have, to figure out our charge, we have a +3 from the aluminum. And then we have 6 hydroxides, and those are each -1. So our total charge on this big complex ion here is 3-. Okay. Oh, and I need a net ionic. The sodium is just a spectator. You should be able to recognize that. So this hydroxide is that. I need to balance, so I need a 3 here. And we're done with the balancing of the reaction. This aluminum with 6 hydroxides is not the most common form. The most common form is actually this. So if you wanted to do that complex ion, that's fine. In that case, you would have only a 1 with the OH minus. It's up to you which one you want to do. But the rule of making the number of ligands twice the charge of the cation works most of the time, and they accept this. This is an acceptable answer here. Okay. If the resulting solution is acidified, we add some H+. With the concentration of the complex ion increase, decrease, or remain the same. So H+, what's it going to do? It reacts with the OH minus. So the reaction is going to go left. So the reaction goes left. And if the reaction goes left, oh, the complex ion concentration goes down. Concentration of the complex ion decreases. You're welcome. Okay, we have hydrogen chloride. Notice it's a gas, so we're not going to split it apart, even though it's a strong acid. Oh, it's oxidized by oxygen gas. Now, oxidized by. So we have to find out what in the HCl can be oxidized. So Cl is -1, H is +1. Oxidation charge goes up. The H cannot go higher than +1, but Cl can. So the Cl must become Cl0. Always check your Hofbrinkel, so it's Cl2. And what's left? Well, the H does not change, so it's going to be the H with the oxygen, and when you have H with oxygen, you have H2O. Okay, there we go. Let's balance it. We need 2 of those, and we're good. Okay, we're done. No worries. Okay. 3 moles of hydrogen. No. 3 moles of hydrogen chloride gas. 3 moles of oxygen react completely. Just think of this as your ICF. Okay, well, you don't even need to do an ICF. You see that you need 2 HCl's for 1 O2. Need 2 moles HCl per mole O2. So we need 6 moles HCl per 3 moles O2, which is what we had. I don't have 6 moles, I only have 3 moles, so the HCl is going to run out. Only have 3 moles HCl, so HCl is limiting, and O2 is excess. And I think, yeah, it's present in excess. We're done. Okay, solid. Potassium oxide, check your charges. Note that it's solid. We are not going to split it apart because it's solid. Is added to water. Now you need to notice you've got a metal oxide. Metal oxides and water make, do you remember? They make metal hydroxides. So we're going to get KOH, check our charges, +1, -1, formula is good. Then you check, do we need to produce hydrogen or not? We only make hydrogen when there's a redox reaction occurring here. Well, in K2O, the K is +1. In KOH, the K is +1. We didn't have any oxidation or reduction occurring. Therefore, we don't need hydrogen to be produced. So we leave this as is in terms of the products, but we need to balance. There we go. And then we shouldn't include our charges. Oh, not done yet. Water comes straight down, KOH splits apart. So K2O, H2O, 2K plus, that is an arrow, not a plus sign, and 2OH minus. Okay, done with the reaction. Question, few drops of phenolphthalein are added to the resulting solution. What would be observed? Explain. Okay, we're producing hydroxide, producing OH minus, which is basic. So, phenolphthalein, clear in acid, pink or magenta in base. Therefore, the solution turns pink. And we are done, and we did that in 6 minutes. Yay, we would be allotted 10 minutes. No, we needed 6. Okay, 2009 test. Solid. Iron 3 oxide, O is -2, Fe is +3, so Fe2O3. Okay, they're telling you what happened. It's reduced completely with solid carbon. This iron 3 oxide is getting reduced. O -2 can't go down any further, so it's the iron that's getting reduced. Completely means to just Fe0. Now we want to see what else will we have. Well, we've got carbon and oxygen left. They have to join together. And you want to figure out, well, what's the common thing? CO, carbon dioxide, CO2. Now, we have to balance. Don't forget to balance. We have a 3 and a 2 for the oxygen, so I need to put a 3 there and a 2 there. And I have 4 Fe's. And I'm going to erase the charges, because those should not be showing. 0, charges of zeros, it's okay to show those. All right, what is the oxidation number of carbon before and after? Before, oxidation of carbon is 0, and after, the oxidation number of carbon is, O is -2, so the carbon is +4. +4. Let's erase our charges there. We don't want that in our answer. Done with that one. Okay, this is important to pay attention to. Equal volumes of equimolar solutions. Well, solutions, we know everything's going to be soluble. We have ammonia, you better know that that's NH3, and we have HCl. We know that's going to split apart. All right, you better recognize you got an acid-base reaction. NH4 plus Cl minus. The H just transfers from the Cl, HCl, over to the NH3, and we get NH4 plus. Now the H and the Cl split apart, so we're not going to care about those Cl minuses, because they are just spectator ions. There's our net ionic equation. And this is not a reversible reaction, because we are adding a strong acid to a weak base. This reaction goes to completion. Equal volumes of equimolar solutions, and they want to know, is the resulting solution acidic, basic, or neutral? Okay, equal volumes of equimolar. Let's just call it 1, equal volumes, equal moles. So 1 mole, 1 mole. So if I start out with 1 mole of each, notice neither is limiting, so they're both going to go down by 1, up by 1. This started out at 0, 0, 0, up by 1. So all the H plus and NH3 are used up. Only ammonium ion is left. And hopefully recognize ammonium is acidic. Therefore, the solution is acidic. End of story. We're only at 10 minutes. We've already got 5 reactions done. We're averaging 2 minutes apiece. Okay, solid. Notice that's solid, so we're not going to split this stuff apart. Mercury 2 oxide, so that's our formula. When we add up the charges, that make them add to 0. And that stuff is solid. It will come straight down. Oh, we don't even have any, no water. Nothing's going to split apart. The only time we will split things into ions is when reactions occur in solution. It decomposes as it is heated. So decompose, the only thing that can happen is it breaks apart into its elements. Don't forget to always check Hofbrinkel, O2. That's it. That's your reaction. Now we need to balance it. 2 and 2, we're balanced. That was easy. Okay, in a fume hood. Why did we do this in a fume hood? That mercury is really dangerous stuff. We do not want to be breathing that. Why would you do this anyway? Why would you heat that? All right, don't worry about that. After the reaction is complete, the mass of the material in the test tube, is the mass of the material in the test tube greater than, less than, or equal to? Well, this all started out in the test tube, and this is what we end up with in the test tube. Oxygen's a gas. What do gases do? They escape. So the test tube material mass decreases because the oxygen gas escapes. You know, we do have conservation of mass. The total mass of mercury and oxygen that was produced will equal the total mass of mercury 2 oxide that we started with, but some of the oxygen actually escapes. Okay, barium nitrate solution. And so we know the stuff splits apart, and I noticed the nitrates, so I'm automatically just going to write Ba2+, and I'm going to hope that I'm not going to worry about the nitrates. A potassium fluoride solution, and potassium, I'm not going to worry about the potassium because K+, alkali metals, always soluble. So I'm just going to worry about the fluoride for now, and I'm going to keep reading. These are combined, and a precipitate forms. We know there's a precipitate. There's only one possibility. Ba, F2, balance, we're done. That was quick. Okay, equimolar amounts. We're just going to pick a random number. Just pick a number. 1 and 1. Equimolar amounts of barium nitrate and potassium fluoride are combined. Which reactant, if any, is limiting? Explain. Okay, now just looking at your coefficients here, 1 to 2, we need 2 F minus for each Ba2+. So do you see right off the bat the fluoride is going to be limiting? So F minus or KF, because they want to know which reactant. Read carefully. They said our potassium fluoride versus barium nitrate. They didn't ask about the ions, they asked about the whole compound. So KF is the limiting. Gosh, I'm wasting time. I'm panicked. I want to finish on time. Write it out, people. Make sure you write it out. Okay. All right, cadmium metal. Cadmium metal is oxidized by adding it to a solution of copper 2 chloride, CuCl2. We know this stuff's going to split. This is going to come straight down. Now, there's a shortcut here. I'll do it the long way, and I'll show you the shortcut. Okay. So first off, cadmium will always become cadmium 2. So it will become cadmium CdCl2 and copper. Whenever you have single replacement, the metal replaces the metal. So notice we had an element and a compound. The metals replace one another. Things that could have positive charges switch places. So we get CdCl2, and cadmium is, you should know cadmium can only be +2. It's along with zinc. Zinc and cadmium can only be +2 when they become ions. All right, it's because they're at the very end of that D block, and because of that, well, that's not true because mercury can be 1 or 2, but the idea is you're at the end of the D block, all you can lose are your S's and become a +2 charge. Okay, regardless, these are both soluble. So we get Cd, copper 2+, makes Cd2+, and copper. And that's balanced already. Very good. List 2 visible changes. Okay, color changes. copper, 2 plus to copper. So the blue color disappears. And the cadmium is sort of a silverish color, so the cadmium silverish metal dissolves, or looks like it goes away, and copper colored metal appears. So we'll have a dark blacky silver metal disappearing, a copper colored metal appearing, and the blue color of the copper ion disappearing. That was 3 things. I had mentioned that I would show you the shortcut version of doing this, so I'm going to erase all of this. And the shortcut way. Okay, so I read this and I see I have cadmium metal, solution of copper 2 chloride. That chloride, I can see right away it's not going to do anything with cadmium because chlorides are only insoluble with mercury 1, silver, and lead 2. So we're not going to worry about the copper. So we have copper 2 plus. And now just looking at those 2 metals, this has to be redox. We have to get cadmium with a charge and copper with no charge. And then cadmium, when it's charged, has a +2 oxidation state. Remember, those charges are your oxidation states. Okay, so that was the quicker path. Last reaction for this year. A hydrolysis, so something's happening with water. Reaction occurs when sodium sulfide, solid, important here, because we're not going to split this apart even though it is soluble. Called solid sodium sulfide is added to water. Okay, so we know that the sodium ion is, well, we don't want to talk about it being a spectator right now. It would split, but it's solid. So it's going to come straight down. And we're told hydrolysis, and they mention pH, so you should recognize this is an acid-base reaction. And we have S2 minus, so that S2 minus is going to grab some H's. Now, I believe they would accept this or this. It turns out HS minus, when it is in water, I'm pretty sure it goes all the way to H2S. But I'm not completely positive on that one. So I'm pretty sure either of those are acceptable. But regardless, we're going to get HS minus plus OH minus plus Na pluses. We can't forget about the sodiums. So let's see. We need to balance this out. Our total charge has to be balanced, and our sodiums need to be balanced, and our H's need to be balanced. I think this is pretty darn balanced. So sodiums, we're good, 2 and 2. Sulfides, 1 and 1. H's, 2 and 2. O's, 1 and 1. Charge on the left side is 0. Total charge on the right side is 0. So this, I am 90% certain, is acceptable. Another acceptable response would be this. OH minus plus Na plus. Well, you could write this as NaOH, but I've sort of simplified it and gone a little farther. Hang on, let's not do it that way, just so that we make sure that we're balancing this correctly. So H2S, NaOH, and now we'll balance 2 of those, and it's balanced. But now I need to split these. 2 Na plus, 2 OH minus. So either of those would be acceptable. Okay. Would the pH be greater than, less than, or equal to 7? Hydroxide is produced. Therefore, pH is greater than 7. End of story. All done.